All right, here's a continuation of the example 1 from class 13. Previously, we used the vector math where we used cross products, and then in part B, we did the 3-diagram method. Now we're going to do velocity triangles. This will be a short one. Velocity triangles, I think, are a nice addition to these others as a means of checking. Quite often, if you get a result that doesn't make sense, use the velocity triangles to just double check what the relative motion is between things, just to confirm to yourself or to maybe refute the answer that you got, so that you go back and try to figure out, diagnose where you went wrong. So here was the cross product method. And we had the 3-diagram method. So for the velocity triangles, it's actually better to actually use these diagrams, and then instead of using breaking the thing down into components, what you could do is, based on the angles that you know, is to draw the velocity triangle. So they're very actually really sort of like, it's just an adaptation of the 3-diagram method. You actually have to draw the 3 diagrams to be able to do the velocity triangles. So knowing those 2 diagrams up above, we could draw out for this point up above, we could combine and say, once again, that this is, I think I do it right here. Do I do it? Yep. That the, and by the way, don't have the figure number, so forget him. The velocity of A is equal to the velocity of B plus the velocity of A with respect to B, right in here. And so the unknown that we have when we start with in this original problem, we didn't know the value of A, and we didn't know the value of A with respect to B, but we did know the direction that A had to go right here, okay? And so, and we also knew that this had to be a right triangle. Right, that was one thing. So we actually had this angle, and we also knew the angle that this had to be right here. So we knew 3 things about a triangle, and when we know 3 things about a triangle, we can define the rest of them. That's the idea here. So we use a right triangle to find the magnitudes of VA and VAB. So just by finding the, we could find VAB by taking the cosine of theta, dividing the VB by the cosine of theta. So now we could find what the hypotenuse is. I should go back and point out this equation in terms of the triangles. The idea, or the method I always think about, is that when you do the addition part of this, this goes head to tail right here, right? So we go to VB, its head goes to the tail of this VA with respect to B. The answer of VA goes tail, tail, head, head right here. So using that vector math idea, that's how you write that's how you decide how to form the triangle. And then from the geometry here, we're able to find that VA with respect to B is 1.655, and we are able also to find VA if we wanted to find it. It's 0.6995. And then by definition, we know VA with respect to B up here is going to be equal to omega times the distance, so we can find what omega is. And that was really the big important thing that we were trying to find. That's why we looked at points A and B first before moving on to C. Now to find the velocity triangle of C, we take a look once again at, let's see, well, we don't actually know the direction here, but we do know this, and we do know that, right? And we do know their initial directions. So we actually draw those 2 things separately right here, those 2 arrows, and then we connect them with, because we know how they add together. So even though that's already drawn for you, you're actually taking, okay, here's VB. Here is, we know this angle right here has to be that theta, and this is theta, and this is V C with respect to B. Sorry, I'm drawing it messy. It's hard to write this way. And then, so then we can go tail, tail, nose, nose, and we could find VC. And the equation for that's this. And we can find the magnitude now. Now that we have the angular velocity of 0.4138, and we know this LBC, we can find out what that magnitude of this velocity is going to be. And now we can apply, we got to play a little game with the angles right here. We could say that this right here is going to be 25 degrees right in here. So we can find what this is going to be, and I'm calling it beta right up in there. And once we know, so now that we know that beta, we know 2 lengths and 1 angle of this triangle. And when that happens, we can use the law of cosines. And this is just the law of cosines written out where I have, usually it's v squared is equal to vb squared plus vc with respect to b squared minus 2. Let me write out the law of cosines in case you can't remember that. C is equal to a squared plus b squared minus 2ab times the cosine, and we'll use big C here to represent the angle. That's big C. The big C is the angle. The lowercase is going to be the lengths. But that's what this is down here, just applied to that, and we can see that we get 3.894. Well, if we go all the way back to what we had up in here when we finally got the solution, we can see that's the magnitude that we received. And now that we need to get the angle of the thing too, that could be sort of a pain sometimes, but it's just a little bit more work. By using the law of sines, we could figure out what I'm calling, and I think this is a variation on theta actually, and so that's the angle that's right up in here. But remember that I want to report a quadrant when I give an angle. I want to report a quadrant that's referencing to horizontal. So that would actually, the angle that we're showing here is actually represented for vertical. So I need to subtract that from 90, and then I end up getting the same answer as before. So we'll do this in one more method in another video.